All right, so today for Algebra 2 class, you guys will be learning lesson 4.12, the number e. You guys have been talking about a lot of logarithmic functions, exponential functions. So today we're talking about the number e. Very, very, very important number. And your learning objectives for today is I know that e is an irrational constant like pi that has a value of about 2.718. So that's what you guys are learning about today. Okay, so here we go. Let's get started by getting our pen and moving on to our warm-up. So your warm-up for today says matching situations and equations. So these are all exponential functions, and you have um, four different scenarios. So match each equation. So these are all your equations. So F, G, H, J, and K to a situation it represents. And here you have four situations, 1, 2, 3, and 4. Be prepared to explain how you know. Not all equations have a match. So if you notice, there are 5 equations and only 4 situations. So what you're going to do is you're going to match. So go ahead and take the time right now to match up which equation goes with which scenario. Go ahead and put your answers now. All right, now that you guys had a chance to do this, let's do a quick review of these exponential functions. So exponential functions, we learned, always had to do with the initial amount times either 1 plus or minus r to the t power. And we remember that r stands for our percent increase or decrease in terms in decimal form. So this is our percent in decimal form. So I'm going to put decimal form, right? But we also learned that sometimes we don't have a percent. When we don't have a percent and we have a rate, we say a times the rate to the t power. Okay, so I'm just going to go ahead and put b for the rate. So let's go ahead and work this out. So the first answer, okay, let's talk about the first equation. A scientist begins an experiment with bacteria 400, so that's our initial amount. Bacteria in a petri dish, the population doubles every 10 hours. So this is important because it doubles. The function gives the number of bacteria t hours since the experiment began. Now, in this situation, we know that we have an equation where our initial amount is 400. They did not give us a percent, but they did tell us a rate. A doubling rate means that we're going to multiply, or it's multiplying by 2. Now, here it says every 10 hours, but because they want it to be every t hours, that's going to be basically t over 10. Okay? So if we reduce, this is supposed to be a t. So if we reduce this, this becomes 400 times 2 because it's doubling. To when we divide 1 divided by 10, we get 0.1 t. So in this case, the very first equation belongs to, well, these have decimals here. These have a rate of doubling. This has a 10t. This has a 0.1 t. So 1 matches up with K. Let me see if I have that popping up first. Yes, I do. Perfect. Okay, so that's our very first equation. Now, I'm not going to explain the rest. Actually, I'll explain number 2, then I'll just put the answers for the rest. So number 2 says a patient takes 400 milligrams of medicine. So we know that our initial amount is 400. Now the amount of medicine in her bloodstream decreases by 25%. So automatically 25% needs to be converted to a decimal. And we know that 25% is the same thing as saying 0.25. And because we are decreasing, we're going to go back to this equation and we're going to use minus instead of plus. So we have our initial amount times 1 minus, because it is decreasing, by 0.25 and then every 10 hours. So our hours represent 10 hours. The function gives the amount of medicine left in her bloodstream after t hours. So that would mean t out of 10. So when reduce this, we get 400 times 1 minus 0.25 is 0.75. And then when we reduce this fraction, t over 10, that's the same thing as saying 1 divided by 10, which is equal to 0.1 t. And 400 times 0.75, that's equal to our h graph. Okay? So you would do the same thing. Remember that half-life means half, so it's 1 over 2, or 1 over 2 can be converted to 0.5. And that would actually be the F graph. And then finally, in this case, the population starts at 400. The population is expected to grow. That means we're going to be adding 25%. So inside the parentheses, it would be 400 times 1 plus 0.25, which equals to 1.25. And 1.25, as you can clearly see, would be the G graph. Okay, so hopefully you marked up the correct answer. This was just a review of exponential functions because what we're learning today with the letter E has to do with exponential functions. Okay, so the next problem that we have is what do you notice? What do you wonder? So very simple. A spot of mold. In case you don't know what mold is the nasty stuff that grows on the walls, on, you know, whatever, that something that's getting like rotten because of like water damage. That's called mold, and it's very, very dangerous. But so a spot of mold is found on the basement wall. Its area is about 10 square centimeters. Okay, so that's 10 square centimeters is a very small piece. So here are 3 representations of a function that models a mold is growing. So mold grows after time, especially if you don't get rid of it. Here they give us this equation. A of t is equal to 10 times e to the t power. 10 is our initial amount. E is our growth factor to the t power, which is time. So after 0 weeks, we have 10. After 1 week, we have 27. And now we have this graph. So now you're going to get a chance to type in what do you notice and what do you wonder about this scenario here. Go ahead and do that now. All right, awesome. So now that you had a chance to talk about one sentence on what do you notice, one sentence on what do you wonder, here are a couple examples of things that you should have noticed. So something that you should have noticed is there is an E in the equation. Did anybody notice that? Did anybody notice that we were using the letter E in this equation? Normally, and especially in our previous examples, let me go back, our rates were either 0.5, 1.25, 0.75, 2, and in this case 2, right? But in this problem, we have the letter E as our growth rate. So that's interesting. So I guess the graph looks like an exponential growth. So notice that this is an exponential growth. It is not a line. It's not linear. This is not a quadratic. It's not a U. It's an exponential growth because it starts off low and it starts increasing very, very, very quickly. So the growth function, because the form of the equation is shape of the graph. And finally, looking at the quotients in the table, the growth factor appears to be a little more than 2.7. So what they're talking about there is like if you have 10 in your area of mold is 10 after 0 weeks, the next week it's 27. How do we go from 10 to 27? Well, what they're saying here is they're multiplying about 2.7. Now, how do you go from 27 to 74? So if we get a calculator, 27 times 2.7, that's equal to about close. That's roughly 74. So this is what it's saying that the growth factor is in our table. Now, what do you wonder? Here are a couple of things that you could have wondered. Why is there an E? And what is E, right? So we've been talking about E, like if we already know what it is, but that's basically what today's lesson is. Okay, today we're learning about what is this E and why do we use it. So can we use logarithms with base E? So you guys just came back from learning how to convert exponential functions to logarithmic functions. So how does that work with base E? If the growth factor is more than 2, does that mean that the mold is growing by more than 100% each week? And then is this a realistic model? So these are things that you could have written down as wondering. And basically anything you write down as a notice wonder, you should get the full credit for that. Okay, so now let's get into some real detailed explanations on what is this E. So In this activity, 12.3, we have equations. In this equation, we have 1 plus a tiny number to the power of a huge number. So here are some functions. For each function, describe in words the outputs for very tiny positive values of x and for very large values of x. So they want us to plug in small numbers and see what becomes of this equation. And they also want us to plug in very big numbers and see what comes with this equation. So in order for us to do that, so I'm going to do this section first, and then you guys are going to answer question 2 and 3. So in order for me to answer this question, I decided to make a table. So our first equation, which is a of x equals to 1 to the power of x, and I chose my very small number to be 0.01, which is about basically 1 cent, okay? In case you don't really fully understand what 0.01 means. And the very large number that I'm going to choose is 1,000. So everyone knows 1,000. So think of that as $1,000. Okay? Okay, so now if I were to plug in 1 cent in this equation, 1 to the 0.001, if I were to plug that in, my answer would just be 1. If I were to plug into this equation 1,000, so a to the 1,000 is equal to 1 to the 1,000 power, so 1 to the 1,000 power is just 1. So what this equation is saying, that if you plug in small numbers, you're going to get 1, and if you plug in big numbers, you're going to get 1. So that's very interesting. Okay, for equation b of x is equal to negative x, when we plug in a very small number, we get negative 0.01. If I plug in a very big number, I get negative 1,000. So what this is saying, it's because the value of the input is a negative. What this is saying is if you were to plug in a small number, you're going to get a bigger number than if you were to plug in a big number, then you'll get a smaller number. In other words, you would rather owe, because think of negatives as owing. You would rather owe 1 cent, right? 1 cent than owe $1,000. Okay, so this is interesting because basically it's inverted. If you plug in a small number, you technically get a bigger number. Then when you plug in a big number, you get a smaller number. So the next equation, 1 over x, when you plug in a very small number, so like for example 1 cent, so 1 divided by 0.01, you get 100. If you were to divide 1 divided by 1,000, you would get 0.001, not even 1 cent. So the output for these very small numbers is that the smaller number you put, the bigger your answer gets. And the opposite is if you plug in a big number, you end up getting a small number as an answer with this equation. Okay, and then we're going to continue. So this f of x is equal to 1 over x to the power of x. Now this is going to be interesting. When you plug in a small number for x as a denominator and x as a power, you get 1.04712. If you were to plug in a big number like 1,000, so 1 over 1,000 to the 1,000 power, you end up getting 0. So what this is very interesting because basically when you plug in a small number, your answer is going to get close to 1. And if you plug in a big number, your answer is going to get close to 2. Okay, that's how this function here works. This function g of x is very similar, so 1 plus 1 over x to the power of x. If I were to plug in a very small number like a penny, so 1 plus 1 over 0.01 to the 0.01 power, you end up getting, check this out, this answer is almost the exact same thing, meaning that if you plug in a very small number, your answer is going to get very close to 1. Now what happens if we get the same equation and we plug in 1,000, if we plug in a big number? So 1 plus 1 over 1,000 to the 1,000 power. This means that if I were to put this in the calculator, my answer will become 2.7169. Now this number 2.7169 is a very important number. Think of the learning objective that I talked about in the beginning when I was reading out the title of the lesson. All right, so let's move on. So h of x is equal to e to the power of x. Now we're talking about this number e again. If I were to plug in a very small number like 0.01, my answer will be 1.001. Interesting. And if I were to plug in a big number like 1,000, my answer will be way too big for me to be able to fit on this slide. So that's just way too big. But this number is interesting. Check this out. So now look at this. We have k of x, which is 1 plus x, completely different than e of x. But look at what happens when I plug in a very small number like 0.01, like 1 cent. So 1 plus 0.01 is equal to 1.01. What do you notice about this number and this number? Very interesting. And then finally, if I were to plug in a big number, I'll get 1001. Okay, interesting, but it's like whatever. So now that I went over kind of these equations and what happens with them when you plug in small numbers and what happens when you plug in big numbers, now I want you guys to answer this question. It says, remember that E is approximately 2.718. Okay, that's what E approximates to. So now you're going to answer this question. What does the function g, so this is the function g, okay, so we're talking about this function here. So what does this function have to do with the number e? Okay, so go ahead, look at what we did here and type in your answer. Go. All right, so now that you had an opportunity to do that, I want you guys to notice our answer for when you plug in a very small number and when you plug in a very big number. What do you guys notice when you plug in a big number? If you wrote something like, the larger the values of x, the function g is very close to 2.718, which is close to e. So if you wrote something like, when you plug in big numbers for x, your answer is going to get closer and closer to e. Okay, that's basically what it is. So this equation, g of x is equal to 1 plus 1 over x to the power of x, is kind of important. So it's a very important equation for you guys to write down. Not right now, in the next slide, but very important for you guys to know. Okay, now you're going to try and answer question number 3. It says, what do you notice about the relationship between h and k? So this is h and this is k. So what do you notice about these two equations for very small positive values of x? So you're looking at the very small positive value of x. So go ahead and type in your answer now. Okay, so now that you guys had a chance to answer your question or this question, what you should have written is, for very small numbers, they are almost equal. See, when you have e to the power of x and you have 1 plus x, when you plug in very small numbers, look at what happens. Your answers almost end up being the exact same answer. Even though these equations are completely different, when you plug in small numbers for them, you end up getting the same answer. And that's a very interesting relationship you guys have here. Okay, so now that I talked about this is a very important slide. I highly recommend that when I'm done highlighting and I'm done going over all this information, you copy this down in your notes. Trust me, I would not be asking you to do this if it wasn't going to be helpful. All right, so if you are going to copy, a good job. If not, then hopefully you have a good photographic memory. Let's go over this. So this is the lesson summary for lesson 4.12. Scientists, economists, engineers, and others, like mathematicians, often use the number e in their mathematical models. So the question is, what is e? So the letter e is not just a number that we use in math, but scientists, economists, engineers also use this number e. So e is an important constant in mathematics, just like the constant pi. So e is not pi, but e is like pi because they are both constants. And we know that pi is a very important number in geometry. So e is a very important number in, for example, algebra, in different like exponential equations. And then we continue. The value of e is approximately 2.718, just like pi, and e is irrational. Oh, so let me just go say, just like we all know that pi is 3.14, right? So everyone knows that pi is approximately 3.14. So now, from now on, if I ask, or if the teacher asks, what does e approximate to? You're supposed to say 2.718. Okay, so just like you all remember pi, you need to all remember what e equals. And let's continue. So just like pi, the number e is irrational. So it can't be represented as a fraction. So that's very important. So E cannot be represented by a fraction, and the decimal representation never repeats or it terminates. The number is named after an 18th century mathematician. His name was Leonhard Euler and is sometimes called the Euler's number. Very important information. All right, let's continue. E has many useful properties and it arises in situations involving exponential growth or decay. So E is a lot. It's used a lot when we're talking about exponential growth or decay. So E often appears in exponential functions. In upcoming lessons, we will work with the functions that are expressed using E. And now, this is another important point that you need to make sure you copy down or that you remember. When we use larger and larger values for x in this equation, 1 plus 1 over x to the x power, and this is when we use larger and larger numbers, the value of this expression gets closer and closer to E. So the value of the expression gets closer and closer to E. So if I were you, I would to pause this, copy down everything that's highlighted, write it in your notes, keep it forever and ever and ever, and use this when you get stuck and you're working on equations having to do with the function E or with the constant E. All right, so now that we're done with this, go ahead and go back to your code down. Go back to Schoology, do your code down. Good luck with that, especially if you copy down these notes. And after that, you'll be done for today's lesson. Thank you very much. You guys are awesome. Take care, be safe, and like always, good luck with everything. Have a good day, everyone.